Hi, I'm Carter, and this is the story behind my novel soft robotic actuator with computerized control and integrated positional sensors. To best understand the rationale behind this year's project, we first must look back at last year's research. This is a soft robot composed of 3 separate soft robotic actuators. When each of the individual actuators is pressurized, the entire robot curls away from the most pressurized chamber. Pressures can be independently controlled in each chamber to control the direction that the actuator curls in. This allows the soft robot to reach in any direction around its central anchor point. To improve the utility of this design, it is desirable for the actuator to know its position in space. The pressure applied to each chamber gives some rough idea of position, but this cannot be used as a precise and repeatable measurement because the actuators are made of viscoelastic polymers. The viscoelastic nature of any soft robotic system means that it will creep and change position slowly over time while it is under pressure. As this graph shows, the required pressure decreased with increasing number of trials, demonstrating why pressure is not a repeatable metric to measure by and that the actuator was slowly stretching out. A new, self-contained positional measurement system was required. The most obvious choice would be to embed conductive rubber sensors into the walls of the actuator and measure the increasing resistance as the rubber stretches. This would not change the mechanical behavior of the robot by very much. One could then take resistances at several different positions and use these to generate a mathematical model to correlate exact positions with specific resistances of the conductive rubber. However, after measuring the resistance of a length of conductive rubber as it was repeatedly stretched and unstretched by the approximate ratio that it would be in the actuator, it was clear that the viscoelasticity of the rubber made it a very unreliable sensor, as this graph shows. This video is from MIT's Computer Science and Artificial Intelligence Laboratory and was released as a part of a paper published early last year. They're using resistance of a conductive elastomer mesh to measure the small deflections of their actuator. The MIT researchers observed the same unrepeatable, noisy signal from the conductive elastomer as I did. To remedy this, they employed a deep learning and artificial intelligence algorithm to sift through the noise and calibrate their sensor, and were only able to create an acceptable model for small deformations. I took a moment to step back and review the problem, and it became clear to me that although conductive elastomer sensors were attractive for soft robotic applications, they had serious flaws, so I set out to find another solution. Since my robotic design already comprises high modulus reinforcing fibers, I hypothesized that these fibers could be replaced by 2 metal wires that the capacitance could be measured between. The capacitance of this system would be dependent on the position of the wires, so it would be more repeatable from an electrical standpoint and may make a more reliable sensor than conductive elastomer. Using the tape wrapper I built, I began fabricating soft robots with embedded wire wrappings. The wires were spooled off of a roll, passed through an acrylic comb to establish the right spacing, and then wound onto the robot. These are a few of the many iterations of sensorized actuators I built. After embedding 2 parallel helices of wire into the wall of the robot, I was able to successfully correlate the actuator's position with the capacitance of the 2 wires. From this graph of position versus capacitance, we can see that the capacitance did not vary with an increased number of trials in the same way that pressure did, so it is far more repeatable over many actuations. Using the model to calculate the robot's position based on capacitance, electronic pressure regulators like these that I designed can be used to pressurize and depressurize the robot's chambers until they have the proper capacitance and hence the proper position. Over the course of this project, I expanded my knowledge of soft robotics, learned about the dependence of resistance, capacitance, and other electrical properties on the geometry of a system, and designed working electronic pressure regulators. This research culminated in an integrated positional sensor based on capacitance that was reliable over the entire range of motion of my soft robotic actuator. Thank you for watching.